Okay, well, thank you. It's a pleasure really to be here today talking about two of my favorite topics, which is ocean observing and technology. And so I think thinking back on it, I probably should have not used that same title. I should have probably reversed them. And when I made up all of these slides, of course, I was focusing on the ocean observing. I'm going to try to make them about equal, so we'll see how that goes. What I'm going to be talking about are three things. Primarily, the University of Maine's ocean observing system. We always called it UMaine. First, everybody else called it GOMOOS, and now they call it NERACOOS. And that's because those are the ones who put our data out to the public, and the ones that the money comes into, to us eventually, goes through there from NOAA. So actually, you can let's see if I can see anything moving around on here. I guess not. Well, on the left there, you see these large buoys, and these are the buoys for the UMaine, and they've been in the water since 2001 in the Gulf of Maine. In addition, I'm going to be talking next about, I should say these really were the state of the art back then, but that was a long time ago. And unfortunately, in terms of funding, we haven't gotten the funds to upgrade these things. So they were very successful. In fact, there's a lot of places who asked us to build buoys for them as well. I'll say a few words about that later. But we would like to improve these things. And at this point, we haven't gotten the funds to actually improve them as much as we would like to. However, we did have another program here that's called Tempests. And this is another NOAA project in something called SINAR. And the Tempest project really is all about storms. It came up after the Sandy storm. And so as a result, we're studying hurricanes and northeasters. So oddly enough, what we had to do is, this has to be a rapid response. So we can put buoys, and as you'll see later, even gliders, into the areas where the storms are coming. You can imagine that you can't get a ship to go out when a hurricane is coming in. And as a result, we had to make small buoys that we can put out there wherever we think the things are coming ashore. And so we have to be able to do this from a small boat because we're really the only people foolish enough to go out there and meet the storm. So we've been doing that with some colleagues all the way from Maryland all the way up here to the Gulf of Maine. And then finally, I'm going to talk a little bit more about MCAMs. As you can see, MCAMs is all about autonomous vehicles. I'm just going to talk about one of them, and that's going to be the gliders, and I'll try to talk a little bit about some of the new technologies that we're using on these gliders and how we're trying to connect them with the ocean observing system. Why is that? Well, the ocean observing system is based on these data buoys, come in real time, and that's great. They get tremendous data. The problem is that we don't have any information of what's going on between the buoys. So rather than just temporal, we need spatial circulations and other things, and so we'd like to try and connect these two things so we can find out what the spatial variability is in addition to the temporal. So really quickly, I'll try to just show you a few things here. This is the Gulf of Maine, obviously. If you look at all the red dots, those are the first data buoys that we put out there in 2001. These buoys were designed here at the University of Maine. They were fabricated here. They were operated from here. And the data process is going on here, and it's still operating. Not all of them, unfortunately, as you'll see in a moment. But basically, like I said, this was the state of the art at the time, and we are starting to make some improvements on other things like tempests. Basically, these things, we are measuring both oceanographic and meteorological data, and it goes online every hour. But a lot of the measurements are done more recently or more often than that. And so waves we do twice an hour. You need 20 minutes to make the measurements, and about 10 minutes to do the calculations before you can put them out. And we, as you can see on this thing, we also do the wind and also air pressure. We do them every 10 minutes. And then also we do some things every 3 minutes. That's temperature and salinity, because we're interested in internal waves, which I can't talk about today. As I said, these were very successful, and so successful that we had other people ask us to do the same thing. So we're also running another system of buoys down here in the American Caribbean. We have 4 around Puerto Rico and 1 over in the Virgin Islands. We also did another 4 for the Mexicans in the Gulf of Mexico. So just going to tell you just show you a quick picture and try to do this as fast as I can. Basically, this is just one of the buoys. It's about 2.5 meters in diameter. We're measuring wind up at 3 meters, so you can kind of get an idea how tall they are. This one happens to be in Jordan Basin, which is one of the deeper basins. It goes down to about 300 meters. And so we have a number of things. We have all the, I'll show you some more details, but all the meteorological stuff happening up there. And what's really different from this is, as you may know, the NDBC, the National Data Buoy Center, they had buoys out here for a long time, another 20 years before us, but pretty much all they measured was atmospheric stuff and waves. That was it. So we've added all this stuff down beneath the surface in the Gulf of Maine. And I guess to talk about technology, although it's not the newest technology, it's one of my favorites, and that's the what we call the ADCP, Acoustic Doppler Current Profiler. You see that here? Up here at about 3.5 meters, it sends acoustic beams down to the water column. And the beautiful thing about this is that one sensor operates as if it can operate as if it's 128 current meters, all the way to the bottom. And of course, it's not its own weight or anything like that. So it goes all the way to almost all the way to the bottom. There's some problems at the bottom I don't want to talk about today. But basically, this thing has been, that was actually the reason one of the reasons I'm bringing it up. It's technology, and it's the first technology that was involved, that I was involved in. It was actually the first grant that I ever had when I got out of graduate school. And so now it's used all around the world. The 2 engineers that I had working on it became very rich. The first company, I did not. And now there are at least a dozen companies all around the world that make these things. So here's kind of an idea of comparing us to NDBC. You look at the stuff in green, that's NDBC. If you look at the stuff in red, that's UMaine. So that's what we've been doing since that time. Even up in the meteorological stuff, you can see we have visibility. This is really important, especially for the Coast Guard. This really helps them when someone's in trouble. They used to try and sort of fly out there, and if it was too foggy, they'd fly, run out of gas and have to come back. So now they wait until it clears up, and then they head out there. So there's a whole number of things here. We could spend too much time talking about all this. I'll just show you a picture here of the cage. This is the cage up near the surface. And let me just walk over and point. This is also a current meter. That also works on the Doppler system, but these beams are going horizontally. Keeps it from having problems with anything really close to the surface, with reflections and so forth. Then at the bottom here, we have the ADCP. This one only goes down to about 100 meters. Some of the ones we have will go down to about 500 meters. Okay, we have different size ones. And then all this stuff in here are the optical sensors, and they measure a lot of things like chlorophyll, CDOM, and a lot of things about wave absorption and things like that. So there's a lot of stuff going on here, a lot of people using this data, and the beauty of all this is this data is available to everyone, and unfortunately, I'm probably the last person to get a chance to look at this data because we're so busy trying to keep it out there operating. I just want to say a couple of quick words about what some of the science things that we found out about, and then move on into the technologies. So right here, the first thing I'm going to talk about is really just a complaint. If you look at, there aren't too many red dots out here anymore. Okay, so funding decreased so much that we had to remove 5 buoys. You can see 5 green ones out there. Those have all been removed from lack of funding. And to the Canadians here, unfortunately, you will notice that we only had 3 buoys in Canadian waters, and now we only have 1. So if you guys want some more out there, let me know. And hopefully we can do something. If you look at this, I'm showing you the thing I'm most interested in myself is circulation and physical processes. And what you see here is sort of a sort of picture of the summer circulation in the Gulf of Maine. And I just wanted to point out a couple of things. If you look over here, we call this the Eastern Maine Coastal Current. This is the Western Maine Coastal Current. And you see there are a number of gyres here over these deep basins, and another gyre in the opposite direction here over George's Bank. So the big question is, like, other than a physical oceanographer like myself, why would anyone care about this? So here's just one reason. You can see here, this actually is much stronger current than this one. during the summertime. And I could spend the next couple of hours explaining why, but we're going to skip over that and say this is really strong, but look, a lot of it, in fact, most summers, most of it turns offshore here. Why is this important? The reason this is important is because a lot of this water here is really coming from the Bay of Fundy. And what happens is up in the Bay of Fundy, of course, we've got this thing called Alexandrium finduncii, which I'm not very, my Latin is even worse than my English. But anyway, basically that's red tides. And it's very dangerous, as you probably all know. And it's always loaded in this current. So as long as it turns offshore and stays away from the shellfish, then it's not really a big problem for us. As you know, if you eat that stuff, then you can become sick or even die. So this is one of the amazing things about this. Now this circulation, when we first figured it out, was just done by going out in ship a couple of times. We took CTD surveys out here, meaning we measured temperature, salinity, pressure, and all that kind of stuff, density. And then in addition, we put drifters out here, and we figured out this happened. So we knew what was happening, but we only went up there a couple of times. So along comes the ocean observing system, and we've got one buoy in this current, and we've got another buoy in that current. So then the beauty is that what happens after that is you can look at these. Now the red one here is the one that's east of Penobscot Bay. This is how fast they're going. That's the direction they're flowing, towards the southwest. If you look at the blue one, generally the blue one is going a lot more slowly than the green one. Excuse me, the yellow, the green one. You got it all wrong. The red one and the blue one, sorry. And the blue one is usually going slower than the red one when during the summertime. But what you see what happens, it happens every year. Some years they're very different, some years they're not so different. So some years a lot of that current goes through, some years almost none of it goes through, and then what you can see is that when you come down to the fall, they come back together and they both move much more slowly. So it's going pretty fast, almost a half a knot during most years, and that, we can look at this and see how strong is this off turn, and we can start to do some studies upon why this happens, and we're actually still working on that right now. I want to say one more thing about this, and that is the Northeast Channel, which is over here at the end of George's Bay. And what you can see over here is that really this is the only place where deep water can come into the Gulf of Maine. By deep water, I mean water deeper than about 200 meters. Okay, what we have is slope water out there. It's really important for a lot of reasons. When that slope water comes in, it really affects the whole circulation, which is the foundation of everything going on in the Gulf of Maine. But the second thing is, while that water is coming in, it's bringing in nutrients. Those nutrients are coming in from the slope water, down deep where they're down too deep so that the nutrients can't be used up because there's not enough light. So what happens is it comes in here, and there were some studies back in the 90s, showed it's always coming in here on the right side. There's a little bit, these are vertically averaged. There's some going out on this side here, part of this gyre around this, but basically right at the bottom is still going in. So it was always coming in stronger in the winter, in the summer than in the winter. Here's the big thing. The nutrients come in here. They go to these three basins, most of them here and here. And so why do we consider that really important? The reason for that is that when the nutrients come in there, this is the reason why the Gulf of Maine is so productive. Okay, so all we have to do is after the stuff gets in there, this basically becomes a reservoir of nutrients. Okay, and somehow you have to get that to come up. There are a couple of ways where you can have that mixing happen. In the wintertime, you can have convection overturning in the winter in some locations, but not everywhere. This water coming in is so dense that no matter how cold you make that water in the winter, it cannot overturn. Okay, so there's only one way to get all of that, or at least most of that nutrient up to the surface, and that's vertical mixing by the tides. Where the tidal current's the strongest? In the eastern part of the Gulf of Maine. So that water brings it up eventually, and that's why we have plankton, phytoplankton blooming. And so that's how this whole thing works. So the big question is, what happens if this changes? And what happened was when we put this in 2004, all of a sudden we saw a lot of things have changed. The regime has changed. Look here, just ignore everything except the colors. Red means it's coming in like we thought it should, okay? And you see here during the summertime, It's coming in from the surface to the bottom. Below this green line here, this is the slope water. So this is the stuff with all the nutrients. You can see it coming in. However, for the first time ever, we saw during the fall and the spring, the first time we put it out there, it was all coming out. And then it happens essentially every year, sometimes weak, sometimes strong. So everything has changed. What happens? That means all those nutrients in the slope water that's coming in, you can see when this is going the wrong way, it comes down. Okay, so we're losing some of those nutrients before they get mixed up to the surface. In addition, this is right in the Northeast Channel. If you look in Jordan Basin, that year there was no slope water at all. It all disappeared. Okay, so this is another thing this ocean observing system helps us understand what's going on. Let me just say a few quick words here about Sonar the Tempests. And you can pretty much ignore all of this stuff. It's a slide that I used once before, so I'll just say a couple of words about it. This is a small buoy, one that 2 strong men can throw in the water. It's about 1 meter in diameter. The main differences between this and the others are we have to be able to get it out before the storm gets there. We wanted to keep it relatively vertical rather than having it tilt over the way they normally do. And so as a result of that, we have a long well. We have a lot of ballast at the bottom, and the reason is we have a depth sounder on it for the first time. And this depth sounder tells us the change in sea level during the storm. So we see what we used to call storm tide or storm surge, all this kind of stuff. Why do people care about that? Because the big problem is that during these hurricanes you have inundation, flooding, all that kind of stuff. So this allows people to try and do forecasts even before it happens. As it starts to begin, they can see how bad they think it's going to be. I think I will leave it at that, except say a few other things. So if you look over here, this is basically all the electronics. This has been redone. This is what we wished we could redo for the other buoys that have been out there for so many years. Basically, I asked my group for a list of these things that were so important, and they gave me a list so long I couldn't possibly say it today. So I'm just going to mention 3 things. One is we have this new telemetry system. Okay, and basically it uses a really hot. It uses a 4G system that gives you a data network. Basically, it's a really fancy new phone that sends all the data ashore. And so what does it do? It has direct access to the internet. Okay, so what that means is we can send data back and forth, a lot of it really fast and relatively cheap nowadays. And the reason, and what makes this so great, is that we can bring back and forth really high resolution data. We can even we can bring back images, and we can bring back videos. That's something new. But the more important than that, we have a brand new data logger and a control system. And what this really allows, it really simplifies the way. It used to be so hard. Somebody wanted a brand new sensor on this thing. It took months for us to be able to make it work on the buoys. Now it takes maybe a week at the most. Okay, this is a brand new system that does that. And then I guess the third thing I'm going to mention, third out of a dozen they said I should mention, is what we just call the Watchdog System. And basically what this does is it gives us remote access to this whole system here. It's almost as if you're in the lab, and you can do everything except touch it. So when sensors turn off, we can turn off the power, put them back on, reprogram them. Even if the data logger, believe it or not, if it locks up, we can start the whole thing over again. So it really saves us for a lot of data that we would otherwise lose. Very quick, 3 minutes. Okay. So I'm going to skip through most of this. This is another kind of ADCP on the bottom of a glider, okay, sea glider. This one has a little different setup, which I won't mention it to you really, I guess, about why it's so different. But it doesn't use the same transducers that the other ones do. And so we had to do a lot of testing and so forth about it. I'm not going to say a whole lot about it, except the reason we use this one, it has a lot less drag, so it doesn't slow down the glider too much. So we did a lot of work. Here it is off of MDI, beautiful place to work. Here's what we were doing. This is the idea. this glider comes out here, comes down between these two buoys, goes back around, comes down a couple more times. And so we were looking for the place where that current turns offshore. It had never been actually measured in the past. So now we have some measurements of it for the first time. In addition, as you can see, what else happens, other than just making current measurements, we're making temperature, salinity, dissolved oxygen, and what else? I can't even read it from here. I think it's chlorophyll. So you can see, you can put up a nice picture here. You know you have a buoy here, and you get another buoy over there, and you can see the changes that have done over the space during that same period. And then finally, we were looking at the Dopplers itself. This is from the buoy system. These are just the tides, tidal currents going in and out. And then you can see when you're in there in a glider, and the glider is moving around by the currents, it's much harder to measure those currents accurately. Okay, so here it is. Here's the first attempt at doing this. You can see we at least see the tides pretty well. We use a standard system here. It's called a, what the heck is it called? I always forget this word. It's called a velocity inversion. Okay, so you have to do some clever stuff because it's moving around. We use the standard inversion that everybody else uses. Doesn't work as well as we want it to, so we're working on that again. We're going to change that. The main thing is you can see that the tidal currents get stronger as you go up, but use the velocity inversion, and it doesn't get stronger. So we have to fix that. We're already on our way. We think that will be working shortly. That's the first time anyone ever used this thing. Finally, I just want to say one more thing about technology. We developed a wave sensor that did what the most expensive and large ones did. This one was small and cheap, and in addition, it also gives you wave directions, which is the hardest part. We put them in our buoys. They worked great, but then everybody was really interested in it, and they tried and failed, and luckily we were successful. We actually made a wave sensor that can work in a glider, believe it or not. So every time it comes back to the surface to send us back the data, it measures the waves as well. So this is something brand new, and as you can see, Teledyne Webb, who builds the gliders, they're looking for an exclusive license with us so that they can sell these and all their gliders for people who want to send them out in storms and so forth. I'll just show you one quick picture here, which just shows you the first test that we did. And if you look in the green, that's one of our buoys. The glider was fairly close by, and that's in blue, and you can see a really good comparison of the two of them. And I guess that's it.